A 15 kilogram mass is launched from the ground at an initial velocity of 30 meters per second and 53.13 yada 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 degrees, drawn right here. While the mass is moving upward and is 20 meters above the ground, it explodes into two pieces. One 5 kilogram piece lands just below the explosion, 2 seconds after the explosion. Where does the other piece land? Now this is a nice problem because it brings in aspects of physics we have done already. And so I'm going to break it down into a couple pieces. So one, where is the 15 kilogram mass when it explodes? 2. What is the velocity of the 5 kilogram piece just after the explosion? 3. What is the velocity of the other piece just after the explosion? Just after the explosion. And 4, where does it land? We do need one other bit here, and where is the 15 kilogram mass when it explodes, and velocity just before explosion. That noise in the background, if you've heard it, is one of my dogs entering into the room. I need to break this up into pieces because this is a constant acceleration part right here. Acceleration is constant. This is constant acceleration, and both of these are constant acceleration. Now this is not constant acceleration right here at the dealing with the explosion because we are introducing another force involved besides the force due to gravity. We assume that the explosion is instantaneous, and so we don't have to worry about time involved there. So the total momentum should still stay the same. But with conservation of momentum, we really don't care what happens in the middle of it as long as forces acting on it are internal forces, and it's a closed system. Now you might make an argument that it's an open system because the force due to gravity is still acting on it, but I'm going to contend that because the explosion takes place instantaneous, that the impulse from the force due to gravity is therefore 0. Force times time is impulse, and if time is close enough to 0, the impulse is close enough to 0, so there is no noticeable change in momentum of the problem there. So this is a conservation of momentum problem. And so we're going to break it up into those 4 pieces. All right, so it starts out as a projectile motion problem, so let's solve a projectile motion problem. I'm going to establish my coordinate system, I hat, j hat. I guess we're doing the first part here. I have my I hat and j hat equation. Delta S, v initial, v final, acceleration, and time. I know that my displacement is going to be 20 meters because that is stated in the problem. That's the point where it explodes. My initial velocity vertically is going to be 30 times the sine of that 53 point yada 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 degrees. I picked this because it's a 3, 4, 5 triangle. And so the sine of 53 degrees is 0.8. And so this ends up being 24 meters per second. Vertically, this is going to be 30 times the cosine of that 53 point whatever degree angle, and so this will be 18 meters per second. I know acceleration, we assume it takes place on Earth, negative 9.8 meters per second squared, and horizontally 0 meters per second squared because the force acting on it is downwards. Once it is launched, the only force acting on it is the force due to gravity, and that's what we know. All right, so to solve it, I need to solve for time first. Vertical basically constricts time, and then we can go from there. I'm going to be using that the displacement is equal to VIT plus 1/2 AT squared. And so we have 20 is equal to 24T minus 4.9 T squared. It is a quadratic equation, so we'll use the formula. So we have to bring everything to one side. So 4.9 T squared minus 24T plus 20 is equal to 0. I'm going to get 2 solutions here. So the question is, will the 2 solutions both be positive, both be negative, one positive or one negative? Those are pretty much the only choices. I guess it could be 0 as well. And with my 2 solutions, which is the one that I'm going to pick? So Do a small little pause if you need to, but try to think about what the answer is before I actually present the solution. So there's going to be a cut in the presentation, so pause if you need to. So this is negative, so this is 24 plus or minus the square root of 24 squared, technically negative 24 squared, minus 4 times 4.9 times 20, all over 2 times a, 2 times 4.9. So I'm getting 3.833 seconds and 1.0648 seconds. So I have two answers. Which is the correct one? Well, it is this one right here, because remember, this thing is being launched up. What the math sees is I have a parabola, and I'm trying to figure out time at these 2 points right here. It has 2 points. This is when it's moving up. This is when it's going down. And so the first time is the time when it's still going up. So that's the time involved. So this is 1.0648 seconds and 1.0648 seconds. Time is the same. So let's find the missing pieces here. Well, I know what the final velocity is going to be horizontally, because the acceleration is 0 horizontally. My displacement horizontally. So this was my J equation over here. My I side over here. Delta S is equal to VIT plus 0, because acceleration is 0. So this becomes 18 times 1.0648, 19.1664 meters. Vertically, I have VF is equal to VI plus AT. And so this is equal to 24 minus 9.8 times 1.0648. This is 13.565 meters per second. And so I have everything. So this is 19.1664 meters, and this is 13.565 meters per second. All right. Part 1 is done. Next up, what's the velocity of the 5 kilogram piece? That's going to be a very boring problem. So what I'm going to do, the 2 seconds hasn't really affected anything until now. So what I'm going to do is I'm going to go back to the original problem here. And instead of 2 seconds, I'm going to make this 4 seconds just to make it a more interesting problem. So 4 seconds instead of 2, and hopefully I'll remember to put a note in the original problem. And so this is 4 seconds, and so that is 4, and that is 16. And so we end up with 78.4 added to the other side. So I have 58.4 is equal to 4 VI, and VI is 14.6 meters per second. And so VI, so that is how fast this thing is going. It is a positive value, which means it is indeed shot up in the air. So now it becomes a conservation of momentum problem, because I know momentum is conserved, that my initial momentum is equal to the final momentum. I can break it up into my I and J components. My I equation here is, so initially I have a 15 kilogram mass times 18 meters per second, and that's equal to, afterwards, I've got, well, my 5 kilogram mass times 0, because there is no horizontal component to it, and then whatever's left over, it's a 10 kilogram mass times what I'm trying to find out, and I'm just going to call that V1. So my 10 kilogram mass after the explosion, I have V1 and call it V2. My J equation, I initially have 15 kilogram mass going at 13.565 meters per second. And that's going to be equal to 5 times its velocity at just after the collision, which we just found. That's 14.6 plus 10 times V2. And solve. So V1 is equal to 27 meters per second, and V2 is 13.0475 meters per second. And so just after the collision, this 5 kilogram mass is shot upwards, initially at 14.6 meters per second, and the rest of it, the 10 kilogram mass, is being shot primarily horizontally with components of 27 and 13.0475. Those are meters per second. The last piece of it is, where does it land? It's now a projectile motion problem again. So I have our coordinate system here, I hat, j hat, delta S, VI, VF, A, and T. The j direction, it's going to end up negative 20 meters below where it started. Because remember, it explodes at the 20 meter mark and then gets shot off, then the two pieces get blown up. My initial velocity in this piece right here is what we just found out. This was 27 meters per second, and this was 13.0475 meters per second. My acceleration vertically, negative 9.8 meters per second squared. We don't know time. We know this 0 meters per second. And classic problem. So we solve for time and then figure that out. So plugging into the one we've used so many times, plus 1/2 AT squared. And so I have negative 20 is equal to 13.0475 T minus 4.9 T squared. 4.9 T squared minus 13.0475 T minus 20 equals 0. Again, I'll have two solutions. Think about what the two solutions will be sign-wise. In other words, plus plus, minus minus, or plus minus, and which one we want. So time is equal to 13.0475 plus or minus the square root of negative 13.0475 squared minus 4 times 4.9 times negative 20 over 2 times 4.9. And I get 3.751 seconds. And then, all right, so I have my two answers here. And obviously we want the positive one. Again, what the math sees is a parabola, and we are starting here going in that direction. That, with our new setup here, this is where time is equal to 0. And so it's going to land on the positive side. That's the negative solution. Also the negative solution, because it was on the going up part of the parabola, the negative solution magnitude is smaller than the positive solution. So at least it passes that crude check. So we now have the time, 3.751 seconds, 3.751 seconds. And we need to figure out this right here. And so horizontally, acceleration is 0. So it's just going to be 27 times 3.751, 101.277. So the question is, how do we actually answer it? I wasn't specific in this practice problem, but remember that it went 19.1664 meters to the explosion, and this is going an additional 101.277 meters. And so I think it should be in reference to where it initially was shot. And we have 120.4434, not all of them significant, meters from the initial starting point.